how to compute page ranks and how we will use Neo4j for computing page ranks. Have you learned this page ranking? Have you heard about PageRank algorithm? Have you learned this algorithm earlier in any of your other classes? We start with this very first question. What is PageRank algorithm? It was an algorithm created by Larry Page, the co-founder of Google, to rank websites in Google's search results. So you go and search for a web page, you'll get web page ranked in some order, right? Which web page is going to come on the top and what is the ranking for the web pages? So they used an algorithm called the PageRank algorithm. So why this algorithm? It determines the influence of a page by using the influences of pages pointing to it. How influential is one particular web page? It calculates that, and based on that, it arranges the web pages. And it's similar to this. A person having more influential friends will be considered to be influential. So we'll take an example here. We'll visualize this. Say you have many web pages on the net, right? So you have many web pages. And all these web pages are linked together using hyperlinks. So every web page is linked. So we have to somehow compute a score, the influence score for every web page. Say I can give a score for every web page. So based on the score, whichever is maximum, right? 0.4 is maximum. Next comes 0.27. Next comes 0.21. Next comes 0.15. When a user searches for a particular topic, if I have all these web pages mapped to the topic, using these scores, I can just put web page 3 on the top. Next comes web page 4, web page 2, and web page 1. So now the thing is, we need to compute these scores. How to compute these scores? For that, we are going to use an algorithm. That is the PageRank algorithm. And it is an iterative algorithm. What do you mean by an iterative algorithm? This algorithm will run in many iterations to finally arrive at a score. In iteration 1, maybe you got some scores. In iteration 2, again it will refine the scores. Iteration 3, it will refine. Finally, it will come to a score. I mean, the PageRank algorithm is used for computing the page ranks. Instead of saying scores, I'll say page ranks. So when I say you're computing a score, you need a formula for that. So PageRank algorithm uses this formula. So if you want to compute a page rank of any web page, it is equal to 1 minus D. D is called the damping factor. Plus B into page rank of a particular page T1 up till page rank of particular page Tn divided by number of outgoing links for page rank for page T1 and number of outgoing links for page Tn. So let me again repeat this. How you compute the score for a web page? Page rank of any page is equal to 1 minus D. That is D is called the damping factor, plus D into page rank of T1. T1 is nothing but another web page which is actually pointing to this web page. Maybe from T1 you have an hyperlink to the page for which you are computing the score. So it's nothing but page rank of that web page divided by number of outgoing hyperlinks from T1. Plus, like that, you can have many pages pointing to this current page, right? So this is also another page having an hyperlink to this page. So this, the page rank of this page divided by the total number of hyperlinks going out from this page. So that is one formula that they are using to compute the score. This is from the original paper published by Larry Page. So we will now take a look at the definitions in the formula. Say I said nodes T1 to Tn or pages T1 to Tn. What does that mean? And what is this page U? I will maybe show it as a diagram somewhere over here. You have to understand what is T1 to Tn and what is U. So suppose if this is page U, let me just draw it here. This is page U. You call this page U. Page T1 is somewhere over here. This is another web page. So this is page T1. What is this T1? T1 is actually pointing to U. That is the meaning. And what do you mean by C of T1? Like that, page T1 will have pointers to many other web pages, hyperlinks to many other web pages. So all the number of outgoing links is nothing but C of T1. And what is PR of T1? That is nothing but the page rank of T1. So to compute page rank of a web page, we use page rank of all the web pages pointing to it, divided by the total number of hyperlinks or outgoing links from that particular page. So what is TN? TN can be another page. So this can be another page, that is the nth page, which is also having an hyperlink pointing towards this particular web page. And what is T of TN? All the outgoing hyperlinks, total number of outgoing hyperlinks. A summation of all these things into the damping factor plus 1 minus D will give you the page rank of a particular page. So we have to say how to compute this. So you all understood what is T1 and Tn, right? T1 to Tn. These are the pages pointing to our current page for which we are computing the score. What is this damping factor? D is normally set as 0.85 in our calculation. It is also called the probability that a user will continue clicking from one page to another page. So we will, in our calculations, set the damping factor to 0.85 by default. So what is the value of D? 0.85. 1 minus D is the probability that a node is reached directly without following any relationships. Say suppose you take a web page, if you take the scenario, you have so many web pages, right? The probability that any of these pages will be clicked by an user at random, that is given as 1 minus D. What is D? 0.85. So 1 minus D is 1 minus 0.85, that is 0.15. So what is this 1 minus D? It is the probability that a particular node will be selected at random. What is C of Tn? You take any particular page or node, the number of outgoing links from that node. So if I say this node is T, what is C of T? 3, because it denotes number of outgoing links. If I have one incoming link, you should not consider that. Okay. Now let us go to the exercise. What is the exercise is, we are going to use Neo4j for computing page ranks to determine the influence of a node. How your node is more influential in a graph. So for that, we are going to use the PageRank algorithm. But even before that, we have to compute that manually to understand how PageRank works. Say we have used this graph in our earlier class for finding minimum spanning tree and things like that. You are familiar with the graph. Let me explain what this graph has. Nodes by name A, B, C, D, and E. And I have defined the label for all the nodes as location. The label given is location. And all the nodes are connected with the relationship distance. Okay. The relationship name is distance. The label name is location. Every node has a property name. Okay. And this name can be A, B, or C depending on the node's name. So this is how I define this. Now what I want, what I'm going to do is I'm going to compute the page ranks for all these nodes. What is the score for A? What is the score for B? What is the score for C? Ultimately, this graph is nothing but like a graph that you see on the internet, right? Every page is connected to every page. So that becomes a graph. So we are going to use the PageRank algorithm here to estimate the influence of a node or the score for a node. So how this algorithm works is, it works in iterations. Every time we take the formula, we compute the scores for every node, that is iteration 0. Then we'll use these scores and compute the values again for A, B, C, D, and E in iteration 2. So it's like we are refining the values in every iteration. Maybe initially you got all the values to be 0.1, 0.1, 0.1, 0.1. Later on you again ran the algorithm, you got another set of values. So you run the algorithm as many number of times such that the values converge. There will be no more changes to the values. So you run this PageRank algorithm in iterations. So we go to iteration 0. That is the very first iteration. We will compute the PageRank scores for all our nodes. So what is the step there is? See, we are starting the algorithm. Right now, none of the nodes have any PageRank. So what is that we are going to consider here is the probability that any node will be clicked is 1 minus d. So we are going to consider the page rank of all the nodes as 1 minus d, that is nothing but 0.15. So this is the initial score that we assign for all our nodes. Because I told you when you compute page rank for you, you need the page rank for T1 to Tn, whichever that is pointing to you. What are the page ranks for T1 and Tn? These are nothing but page ranks from the previous iterations. Okay. Now I may be confusing here, but at least you understood this. In iteration 1, what we do is we just assign initial page ranks to all our nodes. How do you assign that? It is 1 minus d. The probability of clicking any node, taking any node at random is 1 minus d, that is 0.15. So after iteration 1, this is a score for all the nodes. Now we'll go to iteration 1. What is this? We are going to use the page ranks computed in our previous iteration, and then we are going to compute page ranks again. So this is how we computed page ranks in our previous iteration. Are you all clear how we arrived at 0.15? The probability of taking a node at random is 1 minus d. That was already defined. The damping factor was set to 0.85. So 1 minus 0.85 is 0.15. So now we'll go to iteration 1. We'll start with node A. So what is the page rank for node A? How it is defined? That is equal to 1 minus d plus d into page rank of node T1 pointing to A from previous iteration. So we take a node A, we have to identify all the nodes that are pointing to node A from the graph. So the first step is find all the nodes that are pointing to A in the graph. Let's take the graph. So here, what are the nodes that are pointing or that are incoming to A? Are there any relationships that are incoming to A? None of the relationships are incoming to A. So this entire part will be nothing, right? E into 0, you can say. So what is the page rank for A? It is nothing but 1 minus D plus everything can be 0. I'll write it again. It's 1 minus D plus, because we don't have any incoming nodes, the entire thing here is going to be 0. So it's 0. So it will be finally what? 0.15. So even in the next iteration, the page rank for the node A is 0.15. I see a lot of confused faces. Let me repeat this again for those who are confused. See, how you compute this page rank for A? The formula is actually, it is 1 minus D plus D into, you have to identify all the incoming nodes to A. So if there is an incoming node, then we have to find the page rank of that node from the previous iteration divided by all the outgoing links for that. So we have to use that in the formula. So first thing is we'll check whether there is an incoming relationship for A. When you take a look at the graph, there is no incoming relationship for A. So this entire thing here has got nothing. So it's 0. So only thing we have is 1 minus D plus 0. What is D? 0.85. So the page rank for A after iteration 1 will be actually 0.15. So that is how you compute page rank for A in the next iteration, and finally you enter the value. Can you go and compute the page rank for B in iteration 1? We have already finished that in iteration 0. In iteration 1, what will be the page rank for B? So page rank of B. So let's go and do our first step. What is the first step? Find out all the incoming relations to B. So when you take a look at this graph, what are the incoming relations to B? There is only one relation that's incoming. So which is the node that is actually having an incoming relation to B? A. So this is B. So what is now the formula is, we have to find page rank of D. So page rank of D is nothing but, it's going to be 1 minus D plus D into, we have to find incoming node, that page rank you have to take. Page rank of A, When I say PageRank of A, this value is computed and you have to take it from the previous iteration, iteration 0. Got it? And number of outgoing links for A. So there is one outgoing link, another outgoing link, another outgoing link. So how many outgoing links? 3. Are there any incoming nodes to B? No. So we'll stop a process here. So what should be the value here? This is nothing but 1 minus 0.85 plus 0.85. You have to give me the answer now. PageRank of A from a previous iteration is 0.15 divided by 3. So what is the value here? Quick, compute the values and tell me. So I have given the value here. What is the answer you have received? So it is computed and the final result is given here, 0.1925. That is the value for PageRank of B in iteration number 2, but I have given here as iteration number 1 because we started from 0. Likewise, can you compute the PageRank for C in iteration 1? Can you compute that? So how will you start? You take the node C, you see all the incoming nodes to C. What are the incoming nodes to C? There is a B that is having an incoming relationship to C. There is an A having an incoming relationship to C. So here we have an incoming, here we have an incoming, and here we have an incoming. So what are the nodes that are connected to C with an incoming relationship? D, A, and D. So what is the page rank of C? So if I want to compute the page rank of C, how will I compute that? It is nothing but 1 minus D plus we'll have D into brackets page rank of all the incoming nodes from the previous iteration. So it is page rank of B. So when I take B, how many outgoing relationship exists for B? It's just 1. So we'll say it's 1. And what else? Page rank for A. And how many outgoing relationships for A we have? 1, 2, and 3. Plus, we have to think about D, right? We have to find the page rank of D. We have to take the page rank of D from the previous iteration. So that's the page rank of D divided by outgoing links from D. So how many links we have? Only 2. This is incoming for D. Outgoing is only 2. So we're going to do. So you substitute all the values 1 minus 0.85 plus 0.85 into all the page ranks in the initial iteration was 0.15, right? So 0.15 by 1 plus 0.15 by 3 plus 0.15 by 2, you give me the final answer. So I have done the computations, you can verify, you should arrive at 0.3837. That is the page rank computed for C in the second iteration. So like that we have to keep populating the table. Let us compute the page rank for D. What is the page rank for D? So what is that we have to do? Take the graph. So when you say page rank for D, you can very well go and write this. 1 minus D plus D. What are the incoming nodes to D? There is one incoming and it is from A. So it is page rank of A divided by how many outgoing links from A? 1, 2, 3. So you have 3 outgoing links from A. Are there any incoming links to this particular node D? No. So what should be the value here? 1 minus 0.85 plus 0.85. What is page rank of A? That is 0.15. Say this is from the previous iteration. That is iteration 0 we are taking and divided by 3. What is the answer here? 0.1915 or 25? 25. Okay. Anyway, I have also done the computation. It's there. Can you compute for E? Iteration 1 for E. Can you do that? So in each previous iteration, the value is 0.15. Can you find it for this E? So you again take the graph, go to node E, find all the incoming nodes for relationships for E. One is from C, one is from D. So what is PageRank of E? So PageRank of E is nothing but always this one comes first, 1 minus D plus D. And it is PageRank of C. So it's PageRank of C from the previous iteration divided by total number of outgoing links from C, that is only 1. So you have only one outgoing link from C plus PageRank of D from the previous iteration divided by number of outgoing links from D, that is 2. So you go and substitute the values, 1 minus 0.85 plus 0.85. So you give this. And then you PageRank of C from the previous iteration 0.15 by 1 is nothing but 0.15, and PageRank of D is 0.15 by 2. What is the final answer you are getting? 0.3415. Very good. So what I have received is 0.3412. Anyway, let me erase all these things on the slide. Let's see the answer. So it's 0.3412. So let's go and populate this. So this is for iteration 0. Using these values, we computed iteration 1. Using that, we have to go to iteration 2. Like that, we have to follow many iterations until we come to a state wherein the values converge. I mean, there will be no further changes to the values. So it's like, why to suffer like this? We'll use Neo4j for our computation and verify whether the page ranks are correct. So how can you use Neo4j for this computation? We have to call this algorithm from the algorithm library, that is call algo.pagerank.stream. Location is nothing but the label for all the nodes for which I'm going to use in my computation. Distance is the relationship that's connecting my nodes. And iterations, here when I give iteration 1, it just run it once and give you the value. If I give iteration 2, it will run it twice and give you the value. So number of iterations. Damping factor is 0.85, that we have to assume. And yield will give you the output, right? That is which node ID and what is the score. Since we are not happy with node IDs, we'll call our dot get node by ID, and then we'll pass this node ID. Say if 231 is passed, we'll get the node name, and then we'll get the score out. And we are also ordering the score in the descending order because we want the node with the highest score on the top. So this, if we call on the graph, we should be able to compute the scores. So let's go and check. I have the graph in my database. So return in. This graph I have already created. It's there. So we'll visualize it the way we have it in our. So it's A, D, and I think E is here. C should be here. Yeah. Take some time, but good to see it the way it was on the slide. Okay, so for this we have to compute the page rank. What we have to do is just push this here, not this one. I have to copy this. This query I will copy and then I run. So we'll run it for the first iteration. That is iteration 0. After iteration 0, what was the score of all the nodes? So let's go and check what Neo4j does for us. It's like iteration 1, iteration 0. So it should be iteration 0 here. Let's try this one. So we start with iteration 0, we go to iteration 1, and then we go to iteration 2, right? So when I give iteration 0, you see the page rank for all the nodes is 0.15. because the probability is 1 minus D, 1 minus 0.85. If I want to go to the next iteration, that is iteration 1, according to our table, what should be the scores computed? So you have to verify and tell me whether the page rank is correct. For A, it is 0.15. For B, it is 0.1925. For D, it is 0.1925. For E, it is 0.3412. And for C, it is 0.3837. So that's how Neo4j computes it internally. And you can go with any number of iterations you want. If I give iteration 6 times, it computes and makes the process easy for us. And why we need to compute the scores? As I told you, if you have many influential friends pointing to you, you are an influential person. So who is the most influential person in this particular iteration? It is C. If I want to go with another iteration, that is iteration 2, we'll see whether the influential person changes or is it going to be the same. So when you, after certain iteration, the scores will not change. That will be your final page rank. So when I run the third iteration, you can see here, now E is the most influential person. C is coming beneath E. Because C has the maximum page rank and he is pointing to another person. So this person is considered to be more influential than C. So that is the concept here, and that's how we can use PageRank algorithm inside our Neo4j database. I have used Neo4j for computing iteration 2. Iteration 3 is also done. So this page ranking comes under a concept called centrality algorithms in graph analytics. So a very interesting algorithm.